Ooh, it's scary. It's intimidating. This is a scary, intimidating page. No lie. No lie, only truth. So, here we go. Completely new problem. And now we got to start visualizing stuff. All right, so number 5. 2 parallel wires separated by 150 meters carry currents of 5 and 15 amps in opposite directions. So the currents are in opposite directions. What is the strength of the net magnetic field between the wires at a distance of 40 meters from the 5 amp wire? What is the strength? And remember, we're talking about net magnetic field, right? So, and then distance magnetic between blah, blah, blah. All right, cool. So first, let's set it up, right? So we have 2 wires, just like this. They're separated by a total of 150 meters, right? Now they tell us we have a 5 amp side, so we're going to call this the 5 amp side, we're going to call this the 15 amp side. So they wanted to know the strength of the net magnetic field 40 meters from the 5 amp side. So we know the 5 amp side, the radius is going to be 40. That's a 40. And which means by default, the 15 amp side, the radius has to be whatever's left over. So in this case, it's going to be 110, right? 110. I know it's kind of hard to see. So, and they give us our formula right up at the top. Field equals, that's mu, it's like mu naught or something, whatever. Times the amps, that's supposed to be an I know the page kind of cuts it off on yours, divided by 2 pi r. Okay? So, first thing I'm going to do is I'm going to write my formula. Field equals weird mu symbol times amps divided by 2 pi radius. Now, we know that this symbol, they tell us over here, stands for this, 4 pi times 10 to the minus 7. So let's rewrite it. Field equals 4 pi times 10 to the minus 7 times amps over 2 pi times radius, right? So all this breaks down into this. Boom, boom, right? 4 pi, da, da, da. All right, so what we can do right off the bat is pi cancels out, and this 4 over 2 reduces to 2 over 1, which is nothing. So essentially we have field equals 2 times 10 to the minus 7 times amps over radius. So see how we got here? This to this to this. Now let's plug stuff in, okay? Excuse me. So we have our field equals. So we're going to have to do this twice because there's 2 amps, right? And there's 2 radiuses, depending on which side we do. So let's go ahead and do the our left side first. So that's 5 amps and then 40 meters. So we have 2 times 10 to the minus 7 amps. Since we're using the left side, we're going to do 5 in parentheses divided by our radius. Our left side radius is 40. Bam. So pretty straightforward with that one, right? And this is the easy part. The confusing part is a little bit later. So, let's see. Let's see. I'm just checking my key here. 540. All right. So you do the math. I didn't bring my calculator. So we'll call this B1, by the way. Our B1, if you do the math properly, should be 2.5 times 10 to the minus 8. B1, right? That's this left side. B1, B2. So, hopefully you get this. This is what you should get. Make sure, and remember, in physics, the most important thing is knowing how to do it. The answer is obviously important, but knowing how to get there from A to B is the most important, right? Now we're going to do the right side. So, same formula. I'm just going to start plugging in. B equals 2 times 10 to the minus 7. Our amps on B side is going to be 15, which means our radius is going to be 110, right? Well, how did we get 110? Where did that come from? Well, the whole distance separating the two is 150. From this wire, they said we're doing 40 meters in, which means from this wire it's 110, because 40 plus 110 is 150. So, now, you're going to do the math. This is going to be our B2. You guys got calculators, so make sure you get this right answer. 2.73 times 10 to the minus 3. All right, that's the easy part. The tricky part is how to find the net magnetic field. We know in the right-hand rule states that, so right hand rule. Hopefully you guys can see at least when I move it. States that if the field's in the same direction, it's additive. Field in same direction equals additive. Now this is where it's not tricky, but it's just like, hey, wait a minute. When I read this, it says, yo, the field between the wires that are, sorry, two parallel wires, 5 amp, 15 amp in opposite directions. Well, they say the wires are going in opposite directions, but we have to add this one. So let's think about this, right? We have this wire, and we have this wire. We're looking straight on. Our X is going to represent going towards us. Or excuse me, our circle is going to go towards us, and our X is going away from us. So the right hand rule, it's my right hand. I just cut my thumb today, trimming a tree. It's a little sword. And it put a hole in my roof, so I got a little tar there, but that's okay. We're going to finish this problem. Injured, even. So, again, this is coming towards. This is going away. So, this one right here, our right hand rule states that I'm going to use my right hand for this one. Notice my thumb is going to be the direction of the current, and this is going to be the field. So according to this, my field's going this way. Boom, boom. Now this one, the X wire is pointing away, so the current's going away. So if we do this, it's hard to see. Angle it right. My thumb says going away, which means the field is going clockwise, like this. So because of this, the fields are going in the same direction. And that's what the right-hand rule focuses on, the fields, not the direction of the wires. So the wires are going in opposite directions, but the fields, because of that, they're going in the same direction, right? Hopefully, I know some people are going to be a little bit confused, but remember, your other fingers, your non-thumb fingers, that's your field. Notice how they're going this way, right? Your thumb is the direction of the wire because it's right hand. Wire's coming at you, field's going counterclockwise. Wire's coming away from you, notice these fingers? They're going clockwise. In that case, the fields are going the same direction, which means you add. So you're going to do 2.5 times 10 to the minus 8 plus 2.73 times 10 to the minus 3. No. So our total net field strength is going to be 5.23 times 10 to the minus 8. That's our net field. So we had our field 1. So it's B1 plus B2. I know it's a little confusing, but that's okay. Now, number 6. Number 6 is easy, a lot less work. Repeat the previous problem for the wires if the currents are in the same direction. For the wires carrying the current, excuse me. If the wires carrying the currents are in the same direction. So in that case, this is our wire. We're looking head on, right? Coming towards us, right? Right hand rule. I got my right hand right over this. I'm going to put it up top. So this is the one on the left. Notice the current. This is the wire. This is the current. Our current is going this way. The one on the right. Left. The one on the right, the current is going this way. Because I'm talking about, see, left current, right current. Left, right. So notice the currents are going in different directions. Right? So in that case, because the currents are going in different directions, we are going to, sorry, that's supposed to be at 1 minus B2. And we're going to subtract. So we're going to take our originals and we're going to subtract. And you should get 2.3 times 10 to the minus 9. Right? So hopefully everybody gets that. I put another explanation video on there. Another teacher goes over a different problem, but it's essentially the same setup. It's a little weird, but it's fine. All right, so let's do number 7. 2 long wires are 10 meters apart. So let's do our wires. They're a total of 10 meters apart. Current's carrying 6 and 4 amps. So 6 amps, 4 amps in the same direction. So 2 long wires are 10 meters apart and carrying currents in the same direction. Find the net strength of magnetic field at 3 meters from the 6. So this is 3 meters, which means what does the 4 have to be? If this is 3 and the total is 10, what does the 4 have to be? 7, right? Okay, let's set it up. So same formula, nothing new about the formula. So we're going to go write my formula. B equals mu times amps over 2 pi r. We know we reduce it, so I'm going to kind of sort of skip a step. All right, B1, this is my B1, equals 2 times 10 to the minus 7 times 6, B1, 2, over 3. Sorry, I'm getting mixed up. All right, so my B1, assuming you guys calculate this, why do I keep putting I? B1, not BI. 4 times 10 to the minus 7. Make sure you get this in the calculator. Getting it is the most important thing. That'll tell you if you did your work right, which is also the most important thing. All right, now let's do B2. So we're going to do them both. B2 equals 2 times 10 to the minus 7 times 4, that's our amps, over 7, that's our radius on the 4 side. And we're going to do our math, and our B2 should equal 1.14 times 10 to the minus 7. So we have our B1 and we have our B2. Now, because the wires are carrying the currents in the same direction, it's tricky stuff, right? So like I said, we're going in the same direction. That means we are going to subtract, because the wires are going in the same direction, which means the field is going in opposite directions. So hopefully I said that right. B1 minus B2 equals, do the math, 2.86 times 10 to the minus 7. Bam. All right, number 8. Repeat the previous problem for the currents in opposite directions. If the currents are in the opposite directions, they're going to be additive. 5.14 times 10 to the minus 7. Okay, so no worries. A little confusing, but hopefully you got it. Check that other video out I have on there. It's a different teacher, and sometimes, different people explaining things sort of helps it make sense a little bit. But that's it. That's how to do it. Right hand rule. So remember, if they're both coming at you, just like this. If it's going away, it's like this. Your fingers, your non-thumb fingers, show you the direction of the current, right? All right, so rewatch the video if you need help. Hopefully that explains it. I know it's confusing, but it's really not that bad. All right, guys, there you go.